Well, good morning, ladies and gentlemen. Welcome to the webinar organized by 2W Systems in Flensburg, Germany. My name is Barry Eskes and I will be your host for today's webinar. This webinar has been prepared by Jo Schultke and Barry Eskes. Today we're going to talk about breaking barriers in distribution of µMPX in hardware and in the cloud. We will show you how 2WCom allows µMPX to operate in embedded hardware products and as a cloud application. We will also talk about the transport of HE radio from studio to transmitter, specifically for our US customers. The webinar will take about 20 to 25 minutes. During the presentation, you can ask your questions in the side panel of Microsoft Teams. Please use the chat function. At the end of this webinar, my colleague Jo Schultke from development will be available to answer your in-depth technical questions. Of course, you can also contact us after the webinar by phone, email, or Microsoft Teams. So, what are we going to talk about today? We will start with a brief introduction on 2WCom systems. Then we will let you enjoy a brief flashback in time. We're going to ask ourselves, why should we use MPX over IP transport? Then we will talk about the advantages of µMPX over IP versus satellite versus cloud solution. Next and very important topic is transmission robustness. Jo Schultke will tell a little bit more about that. For radio broadcasts in the USA, how to feed HE radio transmitters via E2X. And most important, answer all your questions. About 2WCom. 2WCom is a German company. We are based in Flensburg, way in the north of Germany. We are over 25 years active in the radio broadcast market and a manufacturer and can also support in system integration. All technology is developed by our own team of developers and our products are manufactured in Germany, so we can really say made in Germany. And we are currently with about 35 people, from which 75% are engineers, so we are an engineering company. Let's fresh up our memory on FM and take a closer look at the MPX signal. The left part of the picture shows the frequency range from 20 Hz to 15 kHz, which is reserved for mono audio. A bit to the right, you will notice the stereo pilot, which is modulated as a 90 kHz carrier. Between 23 kHz and 53 kHz, the left minus right audio component is placed. On the moment your radio detects the stereo pilot of 90 kHz, it will immediately process the mono signal from 20 to 15 kHz and demultiplex it with the left minus right audio component. Your car radio will then switch to stereo mode and you will enjoy the unsurpassed audio quality of FM. At the right side, RDS data is carried over a 57 kHz data carrier. This allows your radio to display station name, activate traffic announcement and, most important, switch your tuner in your car to other FM transmission towers without you even noticing it. It also carries TMC, traffic management information, which is data for your navigation system. As you will understand, MPX is a complex signal form. Even the slightest disturbance will have a huge effect on the transmission FM signal. So we have to be very careful when transporting MPX over IP. You do not have to be worried about this because 2WCom has over 25 years of experience, so you're in good hands. When did we start with MPX over IP? In 2012, 2WCom Systems has introduced the first product offering MPX over E1 transport. E1 was used by virtual all broadcasters using microwave links to connect the studio to the transmitters. E1 offers 2 megabit lines and is a synchronous distribution method, perfect for MPX transport. E1 got obsolete and was replaced by IP. In 2014, we introduced the first MPX over IP system with analog MPX input and output. By using a smart compression technology designed by 2WCom, the bandwidth could be reduced from 3.5 megabits to 1.7 megabits. In 2014, that was a major breakthrough. In 2017, the product was upgraded and digital MPX inputs and output were added to the products. In 2020, 2WCom introduced a completely new designed modular MPX over IP platform, offering an MPX codec, µMPX, stereo generator, RDS encoder, dual IP streaming, and secure IP transport in only one rack unit. In 2022, we proudly introduced µMPX over satellite, including a range of features such as dual µMPX decoding, MPX switching for regionalization, and TS-GPIO forwarding. This year, 2024, we made another breakthrough in µMPX technology. 2WCom moves µMPX into the cloud. This allows the broadcasters to put the whole studio in the cloud and generate a µMPX, which then can be distributed from the cloud to a number of µMPX decoders at transmitter sites. So let's take a closer look at µMPX in the cloud a bit further in this webinar. Bandwidth is very important to the broadcaster, as this has a direct impact on the operational cost. As mentioned earlier in this webinar, uncompressed MPX distribution and even 2WCom's MPX compression does not satisfy radio stations with limited bandwidth. We are facing bandwidths typically between 1.7 and 3.5 megabits per second. µMPX, however, does offer an extreme low bandwidth and good audio quality. So how is µMPX different than other MPX over IP technologies? Well, think of a regular MPX like a CD or a linear WAV file, an audio file, and µMPX like MPX4 AEC compression or other high-quality compressed format. Now, what is µMPX? µMPX was specifically designed to compress MPX in a way that it can be transported over a very small bandwidth. At 320 kilobits, blind listening tests have shown that it's extremely difficult to hear the difference in audio quality between µMPX and non-compressed MPX. Most people even can hear the difference. So how does µMPX offer this high quality at this low bit rate? Unfortunately, the compression method of µMPX is a well-hidden secret from Chimio. Just to give you an impression on how we believe it works. The µMPX encoder compresses the stereo audio, RDS data, and pilot carrier to µMPX format. We believe that the audio component is compressed in the same way as high-quality MPX4 AEC. Furthermore, the 90 kHz pilot carrier is important because it's the cornerstone for MPX. So how is µMPX turned into a standard MPX output? We believe the decompression works as follows. The µMPX decoder received via IP the following components: stereo audio, RDS data, pilot carrier, of course with information on the face of the 90 kHz carrier. Specifically, the 19 kHz pilot carrier is important because once recreated, it becomes the cornerstone for decompressed MPX. The 90 kHz pilot carrier is necessary to log audio and the 57 kHz RDS carrier to the correct phase. Furthermore, the decoder restores audio processing as explained in the previous slide. This is the only way to recreate an MPX output which is exactly the same as at all µMPX decoders. Once the µMPX decoder has restored the original MPX, it can be connected to the transmitter. Since 2WCom is at the forefront of technology, we are supporting the latest µMPX version 4. This includes increased bandwidth up to 800 kilobits, improved signal quality at the same bitrate compared to previous versions. The latest firmware upgrade includes synchronous playout, which means that multiple µMPX over IP decoders running synchronous. We do SFN compliancy, and we also now offer µMPX encoding in the cloud. So that was interesting information about µMPX. Aside from the technical part, let's take a closer look at the operational aspects. It allows the broadcaster to process the audio on one central location, avoids time-consuming trips to reconfigure audio processors at the transmitter site. It reduces the number of equipment and therefore lower power consumption. So this looks like a very efficient solution. All nice and well, but let's first talk about why we should use MPX over IP instead of audio over IP. Let's compare both. Please take a look at the upper block diagram. The most common method of transport until today is audio over IP. Audio over IP is effective and, due to the low bandwidth use, a cost-effective way of feeding audio to the transmitters. Audio over IP requires at the transmitter sites an audio over IP codec, a stereo generator, an RDS encoder, and in many cases a sound processor. So how about MPX over IP? Now we're going to take a look at the lower block diagram. You will notice the difference in equipment at the transmitter site. MPX over IP requires only one unit at the transmitter site because sound processing is done at the studio. Distributing MPX offers a significant reduction in hardware at the transmitter sites and therefore in operational cost. How can we distribute µMPX over IP? Well, actually, there are 4 methods of transport. µMPX over microwave link, over a LAN, WAN or internet, over the satellite, and via the cloud. Yes, 2WCom proudly presents µMPX encoding in the cloud. Just to let you know, it is even possible to transport µMPX over an LTE connection. It's depending on the quality and the reliability of the LTE connection, of course, but it's a good solution. This can also be interesting for those transmitter locations without IP, internet or microwave connection. LTE can also be used as a backup, for example, for satellite. You may notice that we show transport of only 1 µMPX over IP. Let it be noted that both the MPX2C and MPX2DS can decode 2 times a µMPX and therefore can feed 2 separate FM transmitters. Why put µMPX in the cloud? Well, we noticed that more and more radio broadcasters like to virtualize the studio and put it in the cloud. This allows the broadcasters to work remotely and generate their program from any location in the world. A logical step is to bring the distribution also to the cloud. The big advantage is that no special hardware is required and therefore implementation and maintenance is easy. It also saves on energy consumption due to the higher density and henceforward saves on rack space. For example, a hardware-based large DAB distribution system at Akiva in the United Kingdom has moved from hardware solution to a virtualized solution, which reduced the rack space from 400 rack units to only 6 rack units. In that case, it was DAB, so not yet µMPX, but it just gives you an example on how much you can save on rack space by switching from hardware to virtualized solutions. So our esteemed customers from the USA were excited about our MPX2C codec for transporting µMPX. And they also asked about transportation of HE radio. The question was, can 2WCom offer a solution for transport of E2X? E2X is a digital stream which can be used to feed the HE radio transmitters. The answer is yes, we can. For that, we have combined E2X via MPE transport, which are both industry standards. The special 2WCom touch is the synchronization between µMPX and E2X. So how does that look like in practice? Let's look at this on the next slide. Well, this slide looks a bit like the same as the previous pages. The difference is that the MPX2C encoder can ingest the HE radio stream, also called E2X, and transport it in sync with µMPX to the decoder. At the decoder side, the MPX is available for FM transmission, while the decoded E2X feeds the HE radio transmitter. Of course, the Moin cloud-based µMPX encoder can also ingest and transport the E2X HE radio data stream to the radio transmitter. This slide shows studio to only 1 transmission link. Of course, 1 µMPX encoder can feed an unlimited number of transmission sites. So for the next slide, I would like to hand over the microphone to my colleague Joost Schulke. Joost is our software developer and our specialist on synchronization and transmission robustness. Joost, let me bring the microphone to you and present you the next slide.
Yeah, welcome everyone. So I would like to talk a little bit about how we can make sure that we avoid the experience that you probably all have struggled with before. If you move in between 2 transmitter stations, that the audio will skip forward or skip backward. So we provide 2 mechanisms that we can employ to synchronize audio in between transmitter stations. One is based on NTP, which we call synchronous playout, which allows you to synchronize the output of the decoders down to 10 millisecond range and less. It requires access to an NTP server, either on the transmitter sites or a centrally hosted one if you have internet connection from your transmitter sites to your NTP server. And the other one, we can even provide SFN networks when you use 1PPS derived systems. We can also planning to use, for some devices can do it, some others not yet, use PTP instead of 1PPS for more modern transmitter sites that also provide PTP synchronization. So those 2 things will allow you to synchronize your audio and hopefully keep your customers from calling you that the audio is skipping when they move in between transmitter sites. So for transmission robustness, whenever we send packets to the transmitter sites, of course, we want to make sure that there are no gaps, and the internet, and some of you might have to rely using just the internet to get your streams to the transmitter sites. But even if you have dedicated networks, there's always the chance that you will lose packets on the way. So we have multiple mechanisms you can employ. The simplest one is probably dual streaming, where we send one stream over one interface using route A, the second stream over another interface using route B, and then we can at least make sure that we have two different redundant routes to the transmitter side. And you can combine that also with error protections, and we have 4 of them. And you can mix and match them as well. So there's 2 forward error corrections, which are built-in into µMPX. It has its own FEC mechanism. We also provide ProMPX FEC, which you're probably familiar with from MPEG TS transports, but also more modern ones like SRT and RIST, which are close in what they do and how they work. So let's look at the FECs first. So the benefits of using an FEC, as the name says, it's the forward error correction. So you send all the repair data with the streams. So there's not a need to have a backfeed. So you can use it for unidirectional links, satellite links, or maybe you have an asynchronous line to the tower where you can send a lot of data but not receive a lot of data. But they're very good for sporadic packet loss, and they also support dual streaming. But again, if even repair packets get lost, then they cannot cope with that. So, or longer sequences get lost. And they also need more buffering time, so you get bigger delays when you use forward error corrections compared to the other methods we have, which are SRT and RIST. So SRT and RIST work in a different way. You probably all know that TCP connections always combine getting an acknowledge from the sender, I received the packet, and if it doesn't get an acknowledge, it will send the packet again. SRT and RIST work in a similar way, except that there's not a constant acknowledge stream going back and forth between sender and receiver. What happens instead is that the receiver will re-request packets that it didn't receive from the sender, and so you only need to send packets again that were actually lost, which reduces the bandwidth by a lot, because the ProMPX FEC and all these they give you a constant bandwidth increase. You always have to send the FEC data. With SRT and RIST, you only send the data that has been lost. It also supports dual streaming, and you can also combine these with other error protections. There's some caveats you have to keep in mind. So SRT doesn't support multicast, whereas RIST does support multicast. And there's some issues you have to look at when using either or. So I think what you can say is there's no one error protection that is best for your use scenario. It always depends on how is your network, what bandwidth you have, and what error scenarios you're expecting. So what we only can say is, like, if you tell us what your system is, we can provide or probably give you a hint what the best error correction is that you can use, and just contact us and we will try to find the best solution that works for your network. So that concludes the error protection part. Thank you, Barry.
Okay, thank you very much, Joost. So thank you for your contribution on the audio synchronization and transmission robustness. Let's get back to the key question, why µMPX is important, and what about the investment and the capital expenses? Because we talk about technology, but at the end of the day, it has to be invested, it has to be bought, it has to be maintained. So CAPEX shows the investment required to purchase the equipment, and because of our modular and compact design, the MPX over IP solution requires only one unit at the transmitter side. So that's a huge advantage. OPEX shows the costs required to operate the equipment. Because of the reduced number of units, obviously less rack space and energy costs per transmitter sites are required. Also, less units means less rack space rental and maintenance. And let's not forget the impact on our environment, the green footprint. due to the reduced number of equipment, the energy costs are reduced dramatically. In these days, where cost for electricity has been doubled or in even case tripled, this is a very important part when talking about OPEX. Please contact your service provider to calculate the exact saving operational expenses because it differs from any application. Yeah, the cons. Yes, there are also potential threats: bandwidth, audio synchronization, and transmission robustness. And how about HE radio? Well, let's go to tackle that on the next slide. So it was a lot of information to digest, but no worry, we're almost there. So we are now coming to the conclusion of the webinar. Let's recall the pros and the cons of MPX over IP. The pros are very clear. The radio station can make more use of the capabilities of the IP transportation network. Especially the dynamic sound processing at the studio allows the radio station to generate more revenue from the advertisers, while at the same time offering a more dynamic sound for the listeners. Also for CAPEX and OPEX, the new MPX over IP technology brings much benefit. By implementing state-of-the-art error protection, we are able to take away the cons and upgrade your MPX distribution network to an impressive level. The solution to WCOM offers is called a virtualized µMPX codec called MOIN, a µMPX 2D codec, and the MPX2DS MPX over satellite decoder. And let's not forget a very important topic for broadcasters and service providers. µMPX is offered by many vendors and therefore has been established as the de facto world standard for compressed MPX over IP, satellite, and now also in the cloud. So before we go into our Q&A section, we would like to do some advertisement about the NAB in Las Vegas, where we have our own booth. You can, of course, find more information on our website, and of course, feel free to schedule a meeting. So thank you for your attention. We are now going to the question and answer section. So please put your questions in the chat function. My colleague Joost Jultke will be delighted to answer them.
Yes, so we already have one question. Someone missed the beginning. So the bitrate, I'm not sure about FH, but satellite links. So I can't really answer how much you can transport because it depends on the transponders you're using for satellite links, for instance. But like the standard MPX transmission, which used to be 192 kilohertz at, let's say, 24 bits, used to have 3.5 megabits. We were able to reduce that to with what we call 2W compression down to 1.5 megabits. And µMPX you can have down to 320 kilobits, which is still for most listeners sounds very good, but you can increase that to 800 kilobits. So basically, if you can carry 10 µMPX programs in what used to be one single MPX classic transport.
I think it also it's interesting to know if the content is, for example, classical music or pop music. Does that make a difference, Joost?
Not that I know of. So the standard bitrates for µMPX always have, as far as I understand it, music in mind. But I know that Timio is working on even lower bitrates for talk-only radio or mono programs, which is called µMPX Plus. We don't support it officially yet, but we're always working close with Timio. So if that is something that is interesting for you, please let us know so we can look into integrating that as well. And I think those bit rates go down to even 180 kilobits.
Okay. So what happens when the broadcast has a network and they want to deploy it with 2WCOM encoders and decoders, and on a few sites they have another brand decoder, µMPX decoder. Will that work, or what are the consequences of that?
Yes, of course it will work as long as both vendors, that is us 2WCOM and the other vendors, use the standard library of µMPX. The library itself will take care of the decoding, so that is nothing each vendor has to take care of. The only thing the vendors have to take care of that is the transport in between. And so, yeah, we are compatible to other µMPX encoders and/or decoders.
Okay, great. Let's see, are there any other questions in the chat function or F&A?
Okay, so that is what we did for the satellite transport. So we have one system that's being installed by a customer where they transport µMPX inside a MPEG transport stream and send that over satellite. In that scenario, what we do is we put the IP packets into multi-protocol encapsulation, which is a method to transport IP packets inside the MPEG transport stream. And so our satellite receiver is taking those, is decoding satellite signals, taking out the IP packets of the satellite, also the MPEG transport stream, and decoding it as if it was being sent over IP. So yes, that works. On DVB it works, yeah. So we already have one solution for that. And on the other side, we of course have our MPX2C and other devices. They can encode an µMPX stream and also have a TS multiplex option where they can do the other part as well.
Yeah, it also be noted that in France they're now deploying a large µMPX over satellite distribution network from two large service providers, TDF and Towercast. So they tested thoroughly all this, also this solution. So yes, it is a perfect solution also for satellite.
Okay, so the question is if we can inject the µMPX interface on standard µMPX input on transmitter. So µMPX is not an interface as such. It's just a codec library, like an encoder decoder library. Like it's not like MP3, but basically you can think of it as a software library that will just take your multiplex signal on one side, encode it, and on the other side it's decoded, but the output of the devices will always carry just a standard MPX signal. So if your transmitter has either AES EBU, like an AA3 input, or an XLR input analog, or a BNC input, our devices have those outputs. So if they decode µMPX, you can feed that into the transmitter. Okay, so the question is the percentage of distributions between, so like what's the main method of transporting µMPX? Is it more satellite? Is it more IP networks? Before we started our project, I think it was only IP networks. I wasn't aware of any µMPX over satellite implementations. There could be some, but I'm not aware of them. Now that we have the two big operators in France using satellite instead, because in France for some reason it's cheaper to use satellite, or they have better coverage over satellite, let's put it like that. Yep. It's probably shifted towards satellite now. But you can even mix and match. So you could have, they also, what they can also do is have satellite as a main feed and use IP as a backup as well. So you can mix and match. As long as the encode is the same signal. Well, or you have two different encoders, but then you will get a different outcome.
So another question on synchronizing.
Yes. So if I run several transmitters with one program, how to synchronize the audio for all transmitters? Okay. So that is what I mentioned about the NTP synchronization as well as the GPS synchronization. So we have two layers of accuracy when it comes to synchronization. What we call synchronous playout networks, they simply use an NTP service, and they will normally get down the decoder outputs down to a couple milliseconds in between each other. And if you use a 1 PPS signal, you can get it down to microseconds. Basically how it works is you set up a global delay, what we call it, in the encoder. Let's say it's 800 milliseconds. And you have several lines. One is 100 milliseconds, one is 200 milliseconds, one is 300 milliseconds. The decoders will take the timing information from the encoder on the decoder side, and they will delay the MPX signal on all sides to the same instance and output it synchronously. So the transmission delays in your network are totally transparent. The only thing you need to take care of that the global delay is always larger than your largest expected delay on the route, or on the slowest route dictates how large the global delay has to be. But if that prerequisite is okay, then the decoders will all output the same content at the same time, down to milliseconds or even microseconds. And for SFN networks, you would need microseconds. So in that case, you would need 1 PPS. And To add to that, our decoders can also be equipped with an internal GPS. So you can either use an 1PPS input on if you have it already present on your sites, or you can equip them with individual GPS receiver chipsets. So you just need to hook up a GPS antenna to the decoders, and then they will take care of the rest. But that is something we also had for MPX and also µMPX. The SFM configurations is being used already. Okay, so the question is FM radio future in Europe versus DAB systems. So DAB is being rolled out more and more. We have more multiplexes coming online. I can only speak for Germany at this moment. I think the current information we have is that the FM will run at least until 2032. Some provinces in Germany even opted for having it run longer than that. I know some countries have already turned off FM, which is Norway. They moved to DAB completely. So it's a mixed bag. Some countries will extend it, some countries will move over, but I think the acceptance of DAB is still mediocre. Like we do it all the time, and I don't even know a DAB radio.
If I may comment a bit on that, Joost, talking to customers, broadcasters around the world, I would say FM. Well, the official statement is not there. Some countries say 2032 or 33. Unofficially, let's look at a different perspective. In Europe, at least, new cars have to have digital radio from 2021 onwards. So let's take an average lifespan of cars for general people for about 15 years. So that means 2035 is the first moment I would say FM could be switched off. On the other hand, FM is a very robust and a very reliable solution. So what we see in most countries which have both, so for example, France or other countries with both FM and DAB, is that FM is doing the major programs, the key programs. In DAB, they have also the key programs, but also sub-programs, so they can diversify their content. So for example, in the Netherlands, you have Radio 10, and we have Radio 1060s, Radio 1070s, 80s, and 90s. So if I like to listen to music from the 90s, I can tune on DAB on that specific channel. For the end customer, the listener, for example, my wife, I was proudly telling her that I have a DAB radio in my car, and she looked at me and said, "Oh yeah, is that true? I didn't hear that." So most people don't care. They just want to listen to radio. So I think that's an important topic as well. For us, as 2Wcom, we support both. We can support DAB networks and FM, and we are still investing, like µMPX, in development in technology for FM networks. So sorry for the elaboration, but it's more like a strategic situation on how to be at FM and DAB. So
it's a fluid market. There are no clear laws yet, so we just don't know. But as Barry said, we have like 3 multiplexes here that have very small radio stations on them. So DAB might maybe cater towards that market. We just don't know.
Yeah, and I see the last comment, DAB with low bit rate sounds bad. I fully agree. So, but they can also sound very good, is depending on the bit rate. So so
then it's up to the broadcaster how much capacity units he's spending on those programs. Yeah. And if you have questions or you have questions later, you can see our emails here, or you can contact Barry and he will forward them to me. We are glad to answer them. So, or if you don't want to put a question in here, you can send us an email later. That's totally fine.
We will still fight with FM with email. No problem. We have very good contact with Hans van Zutphen from TMEO. So Joost is I wouldn't say in daily contact, but in very frequent contact with him. So if you have any problems, let us know. We will try to solve it. So, Okay, ladies and gentlemen, I think that's about it. Thank you very much for your time. And let me see, we did 39 minutes in total. So I think it's quite good in time frame. So Thank you very much. Don't hesitate to contact us. You can see our contact details in the presentation. And otherwise, just take a look at our website. There's a lot of information. And if you are lucky to visit us in Las Vegas, we're happy to meet you over there. Thank you very much. Have a great day and talk to you later. Bye-bye.